Welcome to Automated Flight Week 7, and in this video we will talk about proportional control. It is the easiest, the most simple controller we can think of, where if we have a system with a certain transfer function where we want to make the system reach a certain, a reference value, where we want the output to match the reference value, the only thing we do is first determine the error, which is the difference between the reference value and the output, multiply this with a certain constant factor, a gain, which we'll typically denote with Kp, and the P stands for proportional, and the gain is typically the letter used for gain, and that is fed into the system. So it's a scaling of the error. Now of course this is a very simple controller, but what I want to show you is that in fact proportional control is rarely used on its own because it has certain flaws. But as an introduction to control theory, it is a very easy way to get a handle on certain very important properties. Now the first example I will be using is towing a helicopter. If you have a helicopter and you want to move it from the hangar to the helipad, or from the hangar to a certain position, you will typically use some form of tow cart. The tow cart has a throttle, which is a rotary knob, and if you turn it, the cart will start to move, and the more you turn it, the faster the cart will start to move. Now, for this example, it is very important that this cart has it's important to know that this cart has a lot of internal resistance, which means that if you turn the knob and it moves and you let it go, it stops almost immediately. So it doesn't mean that once we start moving, it will keep rolling if we turn this thing off. So let's see what happens. So we have a starting position and a certain distance, and if we're far from our target, our error in red will be large. And if we reach our desired position, the error will be 0. So as we move from our starting position to our target position, the error drops to 0. Now, the controller, our proportional controller, will multiply this error with a certain factor, and it can be a small value or a large value, but this is what the controller will do. Our controller output for a given error. Now, if we have the position of the helicopter with respect to the target position in green, where's my green pen? I've lost my green pen. Well, anyway, we'll do it like this. This is our target position. We will see that the error is really big in the beginning, which means that the knob will be turned all the way forward. And that means our helicopter will start to move towards our target position. But as this error becomes smaller and smaller and smaller, the input will become smaller and smaller and smaller too, to the point where at the end the input to the system is so small that it will simply not move, and we will not reach our desired target. That is a problem because we want to get to the end, and of course in real life this doesn't happen, but if we have a simple proportional controller, this does happen, and we can prove that mathematically, because if we have a proportional controller here, we can replace this block diagram with the following, where we have our reference, we have our system, and this will be our closed loop system now, where I have replaced this whole diagram with one block. The transfer function of a system like this is Kp times G over 1 plus Kp times G. Now, we can see that for small values of Kp, that this is not equal to 1. There's always a discrepancy between the output and the input. Well, one solution to this is to ramp up the gain. If we make Kp really large, we will increase this, but we won't quite reach our target. There will always be an error because this fraction will never be equal to 1, so the reference and the output will never be equal to each other. As Kp, well, let's say, well, we'll do a really high value for k. So what happens, so for Kp very large, we get that Kp times g over 1 plus Kp times g. Well, this 1 is rather small compared to this term because we've increased Kp so much that this is almost equal to Kp times d over Kp times g, and that is equal to 1. So one of the solutions is to give an extremely high value for Kp, and we will reach it. Now we also know that in reality, if we look at the controls here, that knob doesn't turn to infinity, so we can never have an infinite gain. But we could say, well, let's increase the gain to as much as high as we can get it. Well, in this system, well, that might work, but let's look at a different situation where we have a car, you've broken down, you need to get to the side of the road, and you're going to push it. And we're going to act like a proportional controller. And of course, we would not do this in real life, but let's act as a proportional controller, which means that the further we are from our target position, the harder we will push. Now, we start at position 0 here, which means that our error is very large, and we start pushing with tremendous force, and we indeed go towards our target position very quickly. But as we get nearer here, well, what is the error? The error is still positive, which means that over the complete trajectory to our target, we are pushing the car. But the car builds up speed. The car has momentum. As we push really hard, if we stop pushing, the car will continue to roll. And it doesn't really matter if we stop pushing, we will overshoot our target, which at that point the error becomes negative, which means we either have to start pulling or round to the other side and start pushing again. Okay, we start pushing, but the same thing happens. The car builds up momentum and we shoot through our target again and again and again, and then eventually we'll reach some steady state. But now we have a situation where we've oscillated, and you can imagine that in a real life situation here, that would not be desirable, especially if there is some house here or something else. So proportional control has two problems. One, if we want to reduce the steady state error, we have to make our gain very large, but if our gain is very large, we might get oscillations. There is a third problem. Let's look at the situation where we have a car or an aircraft with a throttle, and we want to reach a certain speed. Now, when we drive, we know that to reach a certain speed, we have to put our foot on the accelerator. Well, you can't see my foot, but you put your foot on the accelerator in a certain position. But our proportional controller cannot do this. What does our proportional controller do? Well, the error between our speed, let's say we start at rest, and our target speed is very big, so we floor it. And the harder the gain is, the more aggressive the control input will be. But let's take some middle ground. We start to reach our desired speed, and of course the error will become 0 slowly. And so the error becomes, well, let's say we actually reach our target speed, and the error is 0, which means we take our foot off the gas. If we take our foot off the gas, our speed will drop. And then the error will increase. So we put our foot on the gas. It takes a while to speed up again, or the engines take a bit of time to spool up again. And if there's if there's some momentum in the system, we will also all have these oscillations, or we will simply take our foot off the throttle and never really reach it, and we end up oscillating and never getting there. The problem with the proportional controller is it doesn't have any memory. It doesn't know to keep the throttle in a certain position. So there's three problems. Well, how do we solve it? Well, a proportional controller is very simple, and we will use it in the next video to work through a couple of examples, simply to show you the effects of a controller on a system. And just having a proportional controller makes it very easy to describe this system. In reality, we will never use a proportional controller on its own. So what will we use? Well, if we have our reference, and we will still have our error between the reference and the output. We will still feed this back so that we get our error signal. Then we don't use just a proportional controller. So we'll have our proportional controller here, but we will use two other components, and there will be a separate video for that explaining it in slightly more detail. We will also have what's called an integrator, and the integrator integrates the error and ensures that we have a fixed, a constant input to our system. So we don't want an input that drops to zero if the error is zero. It maintains a certain level, so that if we want to reach a certain speed, we will keep a certain constant input. Now there's a third part to this, which is a derivative part. And what the derivative part does is anticipate on what's going to happen. You can imagine if you're driving along and all of a sudden you reach a hill, you will anticipate the error. Well, the error will drop off, will increase very rapidly because your speed will drop off very quickly. And the faster this error rate climbs, the faster your controller can respond to it. So the derivative part ensures that the system responds faster to larger changes. All of this gets fed into our system and we have an output. Now we know in the Laplace domain that multiplying things by s is a derivation, and multiplied with 1 over s is an integral. The integral stores information and the derivative is responds to changes in our error signal. That together will be a PID controller where we have a proportional, an integral and a derivative part to our controller. Well, in the next video we will work through an example for that.